So again, we're trying to see if our model child implementing a particular learning theory about WH dependencies and syntactic islands in particular, we'll see if this model child can learn the target knowledge that real children seem to learn. And we'll have the model child therefore learn from the same kind of input that we think children encounter for the same amount of time that we think children encounter it. What is that exactly? We're going to estimate the input from the child's tree bank, samples of child-directed speech, and the time turns out to be about 10.4 million minutes. Turns out that actually corresponds to about 2.15 million WH dependencies. And let me just walk you through a little bit more about that input and that timing. So we're estimating the input by looking at samples from the child's tree bank, in this case about 12.7 thousand WH dependencies of speech directed at 25 children between the ages of 1 and 5 years old. And this lets us estimate which WH dependencies children hear and how often they hear them. It's the WH dependency distribution. And then we can estimate then the timing, right? How many WH dependencies children hear during the learning period, which if you recall, we said, we're going to guess it kind of ends after age 4, so right before you turn 5 at 60 months. And so when does it start? That's when it ends. So we have evidence that children begin to represent the full structure of WH dependencies, that is WH questions and relative clauses, around 18 months. That's when they can perhaps then reliably process WH dependencies from their inputs. They have from 18 months until just before they turn 5. That's our timing. How many minutes is this? In particular, children are awake for only a certain portion of the day at different ages that we have estimates of. So how many minutes? It turns out this is about 10.4 million minutes. Great. Again, on average, lots of variation, but average kid, fine. And how many WH dependencies is that? We can estimate that too. We actually have estimates of utterances per minute in speech directed at children from different backgrounds. So say an average kid from a high socioeconomic status background household might and therefore encounter 2.15 million WH dependencies. So great. We know about the input. We know about the timing, which is like the number of sort of input samples the kid gets. We also know a little bit about the developing systems that impact the child's intake, what they can perceive from the input, and maybe what also they are learning from, therefore. In particular, one known wrinkle to this process is that children's memory isn't perfect. I mean, human memory isn't perfect, but children's memory is perhaps more imperfect than adult memory, and the point is, it's not perfect, right? So memory, of course, is an important part of many things, including processing dependencies. And children's short-term memory, along with related abilities like encoding information with context, maintaining attention, this develops over time. And so the upshot for our modeled learners is children are not going to be taking in maybe all the WH dependency distribution information that's actually out there in their input signal. Like it's there, but maybe they don't get it all. They don't take it all in. Some parts of any particular WH dependency may be forgotten in the moment. So let's look at what that might be like. So again, here's a sample kind of WH dependency, a syntactic path that corresponds to a particular WH dependency the child might encounter in the input. And this, in some sense, is perfect intake, an idealized version. Like you get everything, get all the structure, got all the words, fantastic. If you forget a little something, maybe you forgot that was like in the past tense, a little forgetting. Maybe a little more forgetting, you forgot some of these, right? In fact, we can investigate memory-impacted modeled learners with a recency effect, a human thing that happens where more recent information is more likely to be remembered, less recent information is more likely to be forgotten. And so this is the particular equation that seems to capture human recency effects fairly well. It involves this parameter alpha. We just, are looking here at 4 particular values. So 0 is like no forgetting, perfect. And these other values just give you, less or more steep forgetting curves, where you're looking here on the x-axis at the position of the item from the end of, in this case, the syntactic path. So C is in position 1, pass to 2, 3, 4, 5. And the idea is the further you get away from the end, the less recent you are, the more likely you are to be forgotten. And how much depends on this parameter alpha, right? And so, you can sort of just see what happens if you're forgetting, nothing versus a little versus a lot, right, from the end. And that's our question then. Can the modeled learner produce the appropriate observable behavior? A modeled learner who's encoding this learning theory, who's subject to these input constraints, these timing constraints, and is trying to produce the observable behavior that we see in humans.